Anyways, so uh, we are get to start with the gas tungsten arc welding processes. You know, GTAW is a fusion welding process, and the normal setup, the arc is between the non-consumable tungsten rod and the work, and the arc and weld pool are shielded by the argon as a shielding gas, and filler metal separately added to the weld pool. And we know the design of the torch, right? The filler metal separately added to the weld pool, like you see in the picture. I just turn on my lesser pointer, right? As you can see in the weld pool, the weld product, this filler metal is separately added, and a welding torch and tungsten rod are cooled by the flow of the argon and the cooling water, right? So this is a typical setup of the gas tungsten arc welding. Now, we also know the electrode geometry for the AC and DC welding. The GTAW is working on the DCEN polarity. Why? The answer is because the heat distribution, the 70% of the heat is at the work side and the 30% balance at the electrode side. So here is the schematic of the flow of the electrons and ions. As you can see, the electrons are flowing from this cathode. Here is the tungsten electrode, and they are bombarded on the material, and the ions gets ejected from this uh, material, right? The materials to be joined. So this is the DCEN normally we are working with, and the alternating current or the balance, as you can see, it is working on the 50 percentage it work 50% electrode. So this is a half of cycle, once half cycle on a suitable frequency, and this is a welding process used for the material of construction like aluminum, like magnesium, like for those materials who can readily form oxides on the surface, because in one half cycle we are going to you know uh, break the oxide layer, and the heat for the fusion is available on the lower cycle. So this is a the electrode geometry. We use the sharpened tungsten electrode for the DCEN polarity, and for the AC welding we use this blunt end of electrode. But remember that for the gas tungsten arc welding, we always use the direct current electrode negative and AC whenever required for metal construction aluminum, right? So we never use DCEP polarity, right? DCEP polarity are for the consumable arc welding processes like gas metal arc welding, like submerged metal submerged or a shielded metal arc welding and submerged arc welding. All right. So this is the penetration profile, picture of the penetration profile. Okay, now we move further. The inert gases used with the gas tungsten arc welding are the argon and helium. So most commonly gas is the argon, and the function of the shielding gas is to prevent the contamination of the molten pool, and it also prevents the oxidation of the tungsten rod, right? So this gas, when come in contact with the arc, forms a plasma and ionized, and it helps stabilizing the arc. And at the same time, this argon gas being cooled cools the welding torch and the tungsten rod. So this GTAW is used for the precision welding of the thin materials. When for the material construction, stainless steel for welding of thin sections, then aluminum and other non-ferrous metals also due to excellent arc control. Used also for the aerospace and aircraft components, extensively for high quality and critical welds. In aerospace applications where structural integrity is very much important, and also used for the food and pharmaceutical industries for hygienic welding of stainless steel piping and tanks, the food and beverage industries and all that, because it produces a clean and slag-free welds, because there are no slag formation in this process. It is a gas-based shielding uh, process technology. Now, also used for the art and sculptures for metal artists by the metal artists and sculptures for control and aesthetic clean words, and also used for the pipe and tube welding in a petrochemical and power generation, and most of the time in the root passes in the pipe welding, and many in the pressure pipe joints where you require high uh, strength in the root passes. So these are all the applications of the gas tungsten arc welding. Now, the limitations of the gas tungsten arc welding means it is a deposition rate, right? Unlike the process like gas metal arc welding or shielded metal arc welding, the GTW has a slower welding speed and lower fielding metal deposition. Secondly, is required high skill level, because the welders both hands are engaged holding a torch and feeding up the filler wire. So it's require eye-hand coordination and control, and it's not ideal for the thick section because of the productivity issues and because of the slow deposition rate and the heat input limitations. So, looking at these limitations, uh, the there are various variants are developed, right, to overcome these limitations of the conventional gas tungsten arc welding. And further, to add into the limitations, it is sensitive to contamination because tungsten electrode is used, and if by mistake carried away into the weld pool, it gives a tungsten inclusion contamination, right? And cost and equipment complexity also. Equipment is expensive and setup is very time consuming. So there are various variants of the gas tungsten arc welding processes are developed, and we are going to see them one by one. The process to overcome the shortcomings or the limitations of this, right? Though first is the uh, the gas GTAW pulse welding. We are familiar with the GTAW pulse welding, right? We know that the many welding sets are now capable of providing a pulsed arc in a very high current pulses, right? Or a lower background current. You can see this peak current, and this is the background current, and the peak current and background current switches over a particular pulse frequency, and the maximum current and the background current duration. The current can be varied to shoot the application. So with some shoot equipment, pulse are shaped and can be varied also. So this use of pulsing allows greater control over the heat input. Here you get the average heat input. You can see IAV. So overall heat input that goes to your material is reduced, and it is very much helpful for welding of the thin um, materials of construction like stainless steels, nickel-based alloy, and you get a very consistent uh, deposition of the weld metal, and it is very suitable for the joining the dissimilar thicknesses joints, and for the unsupported root runs and welding in positions. So you can see the buildup of a bit consisting of these nuggets like this. So here you can see uh, pulse current, background current, and the duration of this. So we can calculate the average heat input by this equation. I average goes for IPTP, means peak current, and the time for the peak current, duration for the peak current, plus uh, background current, and multiplied with the time for the background current divided by the total time, pulse and background. So overall the heat input is reduced. So and the distortion is minimized, and this is a very good technology for the exotic materials and the thin materials, right? So here the video, I'm playing the video. You can see the videos in action. Sorry, there is a advertisement in between. Sorry. So,
Purvesh, there is a no sound in video, so video part you can
o-
skip it.
okay, fine, fine. So video I'm going to explain. So you can have this video on the well.com site. The video is explaining the no GTAW, no pulse GTAW, without pulse GTAW, and with pulse GTAW. Um, and Fine. So now we are going to now again I'm back to my screen. So the pulse TIG is a versatile process for all the position and metal thicknesses. So it's good for the positional welding, pipe welding, and sometimes for autogeneous welding, welding without the filler metal, and welding of materials of different thicknesses. So the materials like stainless steel and nickel alloy can be best welded with the pulse TIG application. And there is a greater control of the fusion and penetration. You can see the 1 pulse per second gives a very better deposition of the molten material, and uh, with a deeper penetration also, and a easier welding process and stable arc. Now next is a hot wire TIG welding. So this hot wire TIG welding is, you can see in this variation, instead of the welder manually feeding the cold length of filler metal, right? Usually 1 meter length, right? So manually, instead of the manually feeding of the uh, uh, cold filler metal into the molten weld pool, here the filler wire from a small pool is automatically fed using a mechanism, right? So that is typically electrically preheated, and it is continuously fed via a contact tube. So at the back at the back of the pool, you can see. So the it is heated by the resistance heating of, by prior to adding to the pool, right? So it will increase the deposition rate, and this can be suitably improve the conventional cold wire TIG welding. So it improves the productivity. So, and you can see the uh, typical setup. You can see the hot wire is feed from this arrangement, and this is the arc, right? So is same as that of the cold or normal wire feed, but the wire is resistantly heated to its melting point, so it facilitates the melting. And special shielding is provided to hot wire, and hot wire TIG combines the precision of the conventional TIG welding along with the production rates of MIG welding. Here, the setup goes like this: from the wire feeder, the wire is continuously feed. It passes through the contact tube, and you can see this wire is being preheated by the AC power source before it gets into the molten weld pool. And this big torch will provide the arc, and it is on the DCEN power supply. And this is the principle of hot wire TIG welding. Now, this is a setup. You can see the video in action. All right. So you have seen that this hot wire is being resistantly heating by the use of the alternating currents, and their magnitude is less than 60% of the arc current. So again, the heat input better control is, and it's also avoids the arc blow. and sometimes it oscillates up to the 30 degree in the longitudinal direction. Such mechanism is also available. So they can control by limiting the diameter up to 1.2. It can be done. So there are videos available on the Welding Institute TWI website. You can have a look of this. And the areas of use are the joint welding and overlay welding. In the video, you have seen a video demonstration of the overlay welding. So it's suitable for the materials like carbon steel, chrome nickel steel, nickel base alloy, duplex and super duplex, aluminum, hard facing with stellites. So you can have a variety of application with the hot wire TIG. Now it can be welding is possible in all position with the hot wire TIG welding. About the deposition rates, you can see the uh, this case study of the overlay welding of the 100% duty cycle welding machine. Here the deposition is kilogram per hour with a filler metal of alloy 6 to 5 inconel in a with inert gas is an argon with filler metal is 1.2 mm diameter. You can see between the uh, you know 200 and 300 amps the cold wire, it means the conventional GTAW has a deposition efficiency ranging from, say, something above 1 to max 2 for the 200 to 300 amps, and for the 300 to 400 amps, it is ranging from 2 to 3 kilogram per hour. But in the case of hot wire, you can see the curve, red curve, right? You can see it's ranging from somewhere from 2.5 to 4 in this current range. And for the between 300 to 400 times, still higher current range, you can see it ranges from the 4 to up to 6 kilogram per hour. So it part something with GMW process. It's a good alternate for the uh, GMW process where you will require deposition rates, right? Here, same comparison goes with the help of the arc energy. The lower curve is for the cold wire. It's max to max for deposition efficiency from 2 to 4 kilogram per hour. But this hot wire can shoot up to 4 to sometimes 8 kilogram per hour. And this dash curve is for the hot wire with the oscillation. It further improves the deposition efficiency over a lower arc energy. Now, deposition rates of various processes, when we compare the hot dip wire with other welding processes like, say, SMAW with a 4 mm electrode diameter, the deposition efficiency 0 to say 2 kilogram per hour with a T cold wire. Here, the efficiency is you can understand the 3 kilogram per hour, but with a hot TIG wire, which is as good as to 6 kilogram per hour. So at most par with the GMW process with use of 1.2 mm diameter, electrode diameter, and with this filler metal and this submerged arc welding with 4 mm filler wire with 400 amps. So you can take it as a alternative to these arc welding processes. And some it is from the data sheet of some manufacturers who have claimed this deposition rates. Now, in short, what is hot wire TIG welding is a modified GTW TIG process with a resistance heated fillet wire. As you know, it increases the deposition rate and productivity, and it provides very precise and arc control with the low dilution. And it's ideal for the high quality and automated welding applications. So the advantages are you can have a high joint integrity and metal deposition rate as compared with the MIG or MMA welding. And so preheating of the wire removes any contaminants, right? And the heat input remains controlled and it gives productivity up to 30%. So there are advantages over manual process like you don't need to change the electrode, right? Electrode is continuously feed from the spool and there is no formation of slag and higher deposition rate. over the make process. They are high welding quality and high grade materials are weldable. And there is no problem of spatter, right? So these are the advantages of the MAG welding or GMAW welding. Now, advantage of the TIG cold wire welding, it increases the deposition rates up to 60 percentage and with the welding speed up to 100 percentage. And you can have a larger deposition volume, 30 to 50 percentage at the same welding speed and amperage. Over submerged arc welding, no need for costly flux powder. So it maintains slight contact to weld pool, but no elaborate accessories are required like we required in a submerged arc welding. So hot TIG wire is now taking uh, place in the market, and we'll see the variety of application where the GTW, hot wire GTW is in action. So only the disadvantage of hot wire being the production is still lower than the submerged arc welding and strip cladding. And there is a problem of oxidation of hot wires, and the reactive metals have to be specially protected by back purge. And the setup and working cost is a little high. So um, there are some technical issues with the hot wire TIG process, like sometimes the arc deflects in the by magnetic field to the wire current. You can see the arc deflects here. Sometimes the wire is detached from the base material, and you have to make the adjustment of the wire to the heating part. But the modern TIG, hot wire TIG welding machines have the improved technologies, and they have overcome these issues. So here are the usage examples of hot wire TIG welding. See in a power station uh, construction, as you can see here for these projects. There are power station construction, hot wire vertical with welding setup, flue gas desulfurization plants, and offshore engineering, automatic overlay welding, then offshore engineering for also internal overlay welding of the wall blocks and the wall bodies, and offshore engineering, you can see uh, in the various overlay. Then in the pipeline construction, tube to tube welding. So major hot wire machines manufacturers are Fronius, Polishot, Magnatec, AMI, Daihan from Japan, MEC from Mac from the India, and Lincoln Electrical. They are uh, a very popular hot wire TIG welding machines manufacturers, providing orbital. Some are providing orbital TIG welding with the hot wire setup also. So next is the orbital TIG welding. It is very popular. It's an automatic process that use for the tube to tube shield welding, and it's a very good, very popular welding process. You can see here for pipe to pipe welding, the welding torch. You can see this pipe is being welded with the flange, right? So this welding head is moving uh, in a circular motion, and it is mechanized. So the butt welding of the tube with the pipe with the flange is done with this setup. So this is a new process variation in a pipe welding. And again, for the tube to tube sheet welding, there is a special machine is available which can make weld at the tube sheet with the tube, and it is popular for the heat exchangers industry. This is used widely. Now, the next variants of the gas tungsten arc welding is activated flux TIG welding. This gas tungsten arc welding is used for the in nuclear, aerospace, power, oil, shipbuilding, and other industries. And it uses a and this technology. A TIG welding process developed in the Pattern Welding Institute in the 1960s. So it is not a new process. It has been patented already and is a feasible alternative to increase the process productivity. The activated TIG process uses a thin layer of the active flux that is applied to the surface before the welding, and this causes a constriction in the arc. So it's basically creating a very constricted and stronger arc compared to the normal arc cone. So it gives a very good deep penetration. And here in the process, you can see the flux. This is a combination of various oxides powders are mixed with the acetone kind of medium. It is being mixed and it is applied over the weld joints before welding using either brush or spray. And uh, this GTW welding is done and the arc is applied on it. So it gives a deeper penetration. Now, with this video, you can see in action. All right. So um, we have seen the process. So this process can enhance the weld penetration up to say 300 percentage. So this activated TIG gives weld metal properties similar to parent metal, and it is less sensitive to cast materials variation when we have composition difference. So this is the process is better suitable and the higher welding speed and productivity and the cost of welding can be reduced by as much as 50 percentage. So you can see the pictures, the conventional TIG uh, process where you see the penetration profile and you can see the using the activated TIG process only simply before welding the various oxides uh, compositions in a paste form is prepared and is being applied on the weld joint and it concentrates the arc, stiffens the arc, and you can have this penetration. So this is a activated TIG process. And here I would like to show one of our investigation using the uh, activated TIG process. There are various sub variants also. This is activated TIG welding where you can see uh, the oxides or the paste is applied on the weld joint. Here you can see it is applied on the either side and it is known as flux bound. Here is a flux zone where we have applied not only one composition of the flux on the weld joint, but on also either side. So these are three, and you can see in the picture, the first pictures where my cursor is hovering. This is a normal GTW process where you can see the depth of penetration is a 3 mm, right? In a 6 mm joint, you can see uh, there is we're using no activated flux. The weld profile is very shallow. Here using the ATIC process, this picture, ATIC process, we could achieve the depth of penetration up to 4 mm, slightly increased. And you can also see the depth to weight ratio, right? So this welding depth to ratios also increases. And here using the flux zone and FB, you can see the good penetration up to 6 mm we could achieve with the flux zone process. So full penetration is achieved using the FZ TIG, and with the FP we could able to achieve only 3 mm, as good as the normal TIG. So you can understand the this effect of these fluxes, particularly the titanium oxide, silicon dioxide, chromium oxide, zinc dioxide, calcium oxide, iron oxide. They have a different, um, uh, sometimes single or in combinations most of the time used, but the compatibility has to be investigated by research work. It varies from different material of construction, from the stainless steel, from the chrome moly steel to carbon steel and whatnot. So we have to check the component compatibility, with a flux with the method of construction. But it can be used in a combination rather than individual. It will give a very good effect on the weld penetration. So there are ATIC technology and flux providers are Ador Welding, Fronius, IIT Madras, IGCAR has indigenous flux development. SF Panasonic, OTC Dahan, and Worldwide Specialty Flux Limited, they are manufacturing and selling the ATIC fluxes. They are used in the BHEL, DMRL, and LNT. So, looking at the productivity comparison, in comparison with the conventional TIG welding, where the weld penetration is up to 2 to 3 mm, passes required are 3 to 5 generally for 10 mm thickness. Here, for activated TIG welding, the penetration is 10 to 12 mm, and the passes are required are less compared to this. And we can also take a speed up to 150 to 250 millimeter minute welding speed. So you can see it's a productive process. Regarding the deposition efficiency with conventional TIG, 60 to 65, but with activated TIG welding with filler, we can reach up to 70 to 75%. It can be used with the autogenous mode without filler metal, and it is very efficient for root passes and full penetration welds. So typical applications of activated TIG welding are for the stainless steels, 304L, 316L duplex stainless steels, cryogenic and LNG vessels, pressure vessels and piping, root welds in pipe joints, and some exotic materials like inconel titanium. And for power plant components, it is in use. So advantages are deep penetration in single pass, reduced joint preparation in groove angle, higher productivity and lower cost, maintains TIG welding quality and less distortion and heat input. But the limitations are you require specific flux to match with the base metal, compatibility. And flux application needs clean surfaces. And it's not suitable for thicker filler passes, but it has limited compatibility with the full automation. So the plasma arc welding, the next variant is the plasma arc welding. You can see the design with the welding torch, right? Here you can see the welding torch is designed so there is a passage for the uh, plasma gas to come out from the this inner nozzle, and you have a very constricted arc. Unlike you see in a normal TIG, it is of cone shape where you have a more cross section. But with compare with the plasma arc welding, you can see with the design with the torch, you can have a very narrow, very stiff arc with the 6 degree mostly, and with the conventional TIG welding, you have arc cone of 45 degree. So you can see in the bottom picture, you can see the penetration profile with the conventional TIG welding and with the plasma arc welding. You have a more deeper profile like this, right? It is because of the you know change in the design and the addition of one more gas, shielding gas, plasma gas in the inner core. So you can get this benefit. So this is a setup for plasma arc welding, where there is a welding console. It is plugged up with the DC power supply. There is a coolant regulator arrangement, and the two cylinders are used for the shielding gas and for the plasma gas separately. And this process can be also mechanized. And plasma arc have non-transferred arc, transferred arc, and semi-transferred arc. You can see in this picture, this in a non-transferred arc, this arc is set up between the non non-consumer tungsten electrode and the workpiece directly. And with the non-transferred arc, you can see the arc is set up between these nozzle and the electrode, right? And the arc is set up like this. So advantages are it's the arc ignition due to pilot arc, and we have a stable arc. This insensitive to changes to torch to workpiece distance. We can have a higher welding speed, less distortion, and due to narrow heat affected zone, right? And one-sided welding possible for thicker sheets, and arc can be controlled using the keyhole techniques, and filler metal is not required, and deeper penetration, and the tungsten inclusions can be avoided. So you can see use the plasma arc cutting action in where sometimes for the materials like stainless steel, this machine can also be used for the cutting operations also, where the stainless steel cannot be cut with the oxyacetylene flame cutting. You need a plasma arc cutting. So this machine can cut up to 150 thick with a 150 kilowatt arc power. So here keyhole fusion welding process is also a one variant of its, right? Now you can see this typical square when we have to weld the square butt configuration using a keyhole plasma welding, where the this hole formation means this molten pool is moving ahead with a hole, and you can thick the uh, you can weld the thick materials in a one pass. So it's also variants of the plasma arc welding, keyhole welding. And the next variants, of course, is not a gas tungsten arc welding, but of any arc welding processes, most of the time successful with the gas metal arc welding and the submerged arc welding, which is a narrow gap welding. You can see the for the high thickness joints that can be welded with a narrow groove welding technology, narrow gap welding technology, where a specially designed torch can access up to the root, and you can see a very thick joints, as good as you can see this thick 4-inch thicks could be successfully welded with a very less requirement of say uh, age preparation. At the same time, less materials, filler metal is used. So it's a very cost effective process and a productive process, and very lower residual stresses because the weld metal volume is less, and better mechanical properties, and it can be used in a broad range. So here is a comparison of one job. You can see is a 300 millimeter thick plates of nearly 4.5 diameter. You can see with the conventional single V joints with a 45-degree in groove angle, you can see weld metal deposition is generally 4,200 kilogram, and you need a 168 shifts. With a double V joints, you can see the weld metal deposition 2,600 kilograms, and the cycle time is you need 104 shifts. So there is a 38% reduction in the weld metal volume. And when you use the narrow gap joints, right? narrow groove welding technology. The weld metal deposition is requires 1,000 to 20 kilogram, and cycle time is only 41 shifts. You can see you have a huge savings in materials, labor, and time. So this is again a modern arc welding technology, but used widely for shipbuilding industries for joining in the high thick pressure vessel parts and thick walled reactors. So next variation in the welding automation is the robotic. You have heard the word of cobot and robot. So now the cobot word is popular among the industries, among the welding industries. You can see the difference between robot and cobot is no, robot is used for the highly structured environments and for automotive manufacturing setup where there is a human interaction. So you can see it's a programmable device where you also required a specialized knowledge and particularly safety, right? You required a safety cages for prevent any injury. And cobot is a very collaborative robot, right? It can work in the lighter assembly, light welding, machine training, packaging, inspection, and it can also work side by side with the operators and it has less programmable complexity and it is a very flexible. So you can see the integration of GTAW welding with the cobot. You don't see any fencing, you don't see any much safety concerns right here. But here you can see with a GMAW setup, with a robot is being used in the fence environment is a programmable. So this is called robot. And for the lighter welding application, for it's known as cobot, use of the cobot. The next variants is a wire and arc additive manufacturing. This where the power source can be GMAW or GTW or plasma GMAW, and the wire feeder units use and can use up to wire up to 1.6 mm. And there are also manipulators are used, six-axis, three-axis manipulators, and it is meant for building the complex 3D parts. So you can see the wire and additive arc manufacturing. The here you can see the with the integration of the welding machine with the computer and controller and the robot, and you can see it is a layer by layer deposition, right? So you can make a deposition of materials in a layer by layer. Direct energy deposition is also known as sometimes. So this technology is meant for building a very complex parts, right? And you can see the WM process in action with this video. Okay. So you have seen this the continuous wire is melted and using the electrical cart and it is deposited on the substrate and the component is built up layer by layer. So you need a CAD model and you need a programmable tool path and a programming technology to do this welding wire editor. So their merits are their high deposition rates are possible, 4 to 10 kilogram per hour, and there is a low material wastage, and is a cost effective for the larger metal parts, and is a flexible material options for the steel, titanium, aluminum, nickel, and suitable for repair and customization. The demerits are their required post processing. The surface finish was not good, so requires side milling or machining, and heat input can cause residual stresses or distortion problem because wire is continuously feed, so you can the heat input could be a problem, and you know sometimes limited precision. So it is also under stage of research, and many researchers across the worldwide are focusing their interest on the wire and LED arc manufacturing process. You can see for the key industries like aerospace, marine, for oil and gas, automotive, defense industries. You can see the structural titanium parts. You can see the propellers. You can see these uh, using the robotic action, the parts manufacturing with this method. This is a built-in parts for the marine and heavy engineering industries, and you can see the in the overlay applications, and this is the aluminum material construction complex parts. So this kind of parts can be made with welding, and later it can be machined. So this is all about the uh, modern arc welding technology. Now, my colleague, Dr. Subhas Das, will take over, and he'll be explaining about the uh, modern arc welding technology used with the gas metal arc welding process. So we can take up the question and answer at the end of the session. So thank you all.
I think the time, I think we don't have time, na, Ankita?
Yes, we have some, but you can explain the
Okay.
GMAW RMD
Uh,
technology if you have time. Yes.
yeah, we have a 5 minutes. Okay, I will just try to
Okay.
Yes, sir.
explain.
If you want to, we can, sir.
Okay,
We have 5 minutes, sir.
5 minutes. Okay, noise. No? Okay, can you see my screen?
Yes, sir, it's visible.
Okay, okay. Uh, Okay, as Purvesh Nanavati explained about all about the GTW. Okay, so definitely none of the process can replace the GTW with respect to the quality. Okay, but when we talk about the productivity, because the industry is always wants productivity. Yes, we also want the quality, but quality, it is okay, you will get with the some technology which is faster, and you are getting the your satisfactory quality, then you can go ahead with the technology. So there is a one technology that it is developed by the Miller. Okay, it is a patented by the Miller. So just I would like to discuss about it. Is called RMD. Nowadays, you can the maximum time you can see whenever you are welding with the stainless steel, the purging is required. Now, this is the technology which is available. There is a no purging is required. Okay, so no back purging is required. Okay, so if we talk about the waveform, like generally when we talk about the waveform, okay, so then GMW short circuit, globular, spray, and pulse. So this RMD comes in the short circuit. Okay, so so Miller has did some modification in this process in these waveforms. Okay, so if we can, this is the waveform of this process. So what they have changed? So just I will explain with this figure. If it is the sort waveform for the normal machines, any XYZ machines, and this is the waveform for the RMD. Okay. So here when you start the welding, the ampere is slowly down during the pinch effect, but in RMD it is down fastly in the pinch effect, so which will stable your arc, or we can say which stable your weld puddle, so you will get the noise patterns. Now what is about the oxides which can be prevent with this technology? So in RMD there is a special kind of nozzle which will provide you localized cloud formation of shielding gas behind the joint, and which will prevent the oxidation. Okay, so I will just run one video so you can understand how it is. You can use this technology without the purging. Okay, maybe you cannot hear the sound, but just I will explain. This is the 4 point. Okay, so now here you can see this is the nozzle, and there is no bed. And this technology is only used for the root welding. Yeah? Here you can see. So it during welding itself, it is generating one cloud. Okay, so this cloud will prevent the oxidation. Okay, so after welding 1 to 3 years, you can get some blackish bead, but that is not oxide. So if you have a after SS, generally there is a process of pickling and passivation. If you do the pickling and passivation of this bead, you will get the whitish bead, whatever required. Okay, so this is the one of the technology. Another technology I just would like to touch about the HD MIG. Okay, so if I will go, then mm, yeah, this is the technology. Okay, so generally, how this technology works? Okay, so it works like the we can say it is a high deposition. Okay, so what is deposition? What amount of deposition? So it can deposit up to the SAW like 9 kg per hour. Okay, so in the GMW with the 1.2 m diameter wire, you can get the deposition up to 9 kg per hour. So this is very good technology. How it works? So it works like this is the we have designed specially kind of nozzle, and Miller designed some special kind of tip, contact tip. Okay, so it is the CV MIG. So this is the typical arrangement. But in the when you go to the HD MIG, okay, you can see the tip is recessed, okay, and the nozzle is extended. Okay, so we have designed some preheated the wire, and also when you preheated the wire, okay, in the GMW, it is very difficult to control the arc. Okay, so that is controlled with the software. So this is the convert into Excel spray, and then we convert Excel spray into the spray mode, and you can get the deposition. So I have did some comparison, so you can understand how it is faster. So with the compared to CV MIG, it is 30 to 40% faster HD MIG. Okay, like if we want to 10 like size fillet weld, in both the case, this CV MIG, this HD MIG, this is shielding is stick out 18 and 13. Okay, so travel speed 250, 375. Okay, so in the CV MIG, to get the 10 weld size, you can achieve 250 per minute, but in the HD MIG, with the same ampere, 300 to 310, 300 to 310, you can achieve the 375 wire, or we can say speed. Okay, so the 30 to 40% higher productivity you can achieve in HD MIG. So if we talk about the groove welding, if we consider 20 thickness plate you have to weld, okay, then you have to fill. In the CV MIG, you have to deposit 10 passes to this 20, while in HMIG only passes deposit the 20. Okay. So in both the cases, you can increase your productivity with the quality.